So during the break, there was one question from the student. What does the hat means? So whenever I write a capitalized letter with this triangle called hat, it means I'm writing the parameter in the frequency domain using phasor representation. Okay. So I tend to use lowercase letters like this one, lowercase I, lowercase b to represent the parameter in the time domain. But after I transform to the phasor representation into the frequency domain, I like to use capitalized letters and then to add the hat to more pronouncedly state it's working in the frequency domain. I'm walking back anyhow. Alright, so let's continue. So eventually, we performed the real spatial derivative for the generalized solution form, and I can link that to the KVL equation. Now I can compare turn by turn. The yellow ones, they are equal. The green ones are equal. So I now have these two relationships. So somehow, voltage amplitude in the positive direction is related to the current amplitude in the positive direction and is linked by the complex propagation constant and this resistance inductance. So basically, whenever you determine the working frequency, this is a constant. So this is telling you, once you know V0 plus, you already know I0 plus. By the same meaning, when you know V0 minus, the backward propagating voltage amplitude on the transmission line, once you know the parameters of your transmission line, you know its corresponding backward propagating current amplitude. So this is a very beautiful message. This is telling you after we take more detailed examinations, initially we thought we need to solve for 4 unknowns, but eventually we only have 2 unknowns to be solved. Once you know voltage, you know current. Okay? Provided that you really understand your transmission line. So if you know your gamma, basically you know how voltage and current are related for a certain direction. Okay? So this is the beauty of a transmission line. So let's take a look. I performed detailed derivation for you. So from the first equation, I can have V0 plus divided by I0 plus. This is what I intended to define because V divided by I is your impedance. Okay? So now from this, I can have V0 plus divided by I0 plus, which should be my forward propagating characteristic impedance. This, after some messy derivation, I have basically a pretty nice result. Square root of R prime plus J omega L prime divided by G prime plus J omega C prime. Okay. Now the bigger question is, what about V0 minus divided by I0 minus, right? If they're equal, then we hit the jackpot. So eventually, after the derivation, remember, there is an additional negative sign, but the value is the same, only differing in the sign. Okay, so which is really not too bad. Okay, so let's define this as Z0 and define this as negative Z0. Now you have to think. How can impedance takes a negative sign. So what I'm saying is, on the transmission line, okay, the same transmission line, the ratio of V0 plus to I0 plus will be equal to Z0. So these are also determined, provided by the transmission line. For a transmission line, you have to know R prime, L prime, G prime, and C prime. So after you know all these four, 1, 2, 3, 4, you know all these four parameters, you know gamma. You know the complex propagation constant. And also, once you know these four parameters, you know the characteristic impedance. Okay. So for a given problem, those will be provided for you. Z0 probably provided for you, gamma probably provided for you. And once you know gamma and Z0, you know basically everything for a transmission. And once you know that, and if you know voltage amplitude, you know the current amplitude. Okay. So you only have the voltage amplitudes remain solved. But now the issue is the positive voltage divided by the positive current amplitudes is indeed the characteristic impedance. It's provided for you. It's a transmission line parameter. But how can the negative propagating wave, the negative voltage amplitude divided by the negative current amplitude, is picking up the same value but with a negative sign? How can you explain this? I mean, or do you accept it? Do you embrace it? Just like I told you? I mean, having a negative sign is fine. Do you think it's fine? So this is really saying that I0 plus is V0 plus divided by Z0. I0 negative, I0 minus is negative V0 minus divided by V0, Z0, sorry. So remember, if you can accept voltage divided by current is taking on a negative sign, then the generalized solution form is now written in these two equations. Okay? Voltage remains the same, but current is represented again by voltage. But you only have to divide by zero. But remember, for the negative propagating current wave, you have a negative sign. So let's talk about what's the reason behind this negative sign. One potential reason, very evident reason, is Professor Huang did it wrong. I made a mistake. Okay, it's shooting. But what if I'm not wrong? What does the negative sign mean? So this is telling you I0 plus is equal to V0 plus divided by Z0, and I0 negative, the negative current amplitude is the negative of V0 negative Z0. While you are thinking, does it make sense for us to ask, why do we have a negative propagating wave on the transmission? Now, if we understand that, we will understand the significance of the negative sign. So, the question now is converted to where does the negative propagating wave come from? So let me show you the transmission line. Right? So we have a transmission. I have a very long transmission line. I have my user at Tsinghua University. High power is generating the power from some kind of dam. Okay. After the generation of power, they deliver to us for a very long transmission. So ideally, high power only wants to deliver the power to us, right? So ideally, on the transmission line, I should only have the forward propagating voltage and current. So how can there be backward propagating wave in the form of voltage and current? It is because we, the users, are very naughty. We never listen to teachers, right? When teachers send in the information, the knowledge, we usually don't absorb them. We bounce them back, like what you're doing now. Right? The TA is laughing. It's also my graduate student. Think of the delivery of energy on the transmission line as I'm trying to teach knowledge to you. The best situation the student and teacher could ever dream of. I send in knowledge, I teach you knowledge, and you completely absorb the things I teach. In that case, the transmission line has only forward propagating wave. But you might be sleeping, right? You might be sleeping now, so my knowledge to you are somehow bounced back and returned to me. So as I'm teaching myself. I'm understanding the transmission line more and more. Each year I'm better and better. Is that the situation? There's no response, so 100% absorbed. There's only forward propagating knowledge in our class. Okay? So the reason is you might have the so-called impedance mismatch. The transmission line is represented by its characteristic impedance. For example, might be example Z0 equals 50 ohms. This is a very particular transmission line. So I have a 50 ohm characteristic impedance transmission line connected to a 100 ohm load. 50 does not equal to 100, so partially some of the voltage, some of the current, and some of the power are reflected back. So therefore, you have input forward propagating waves, and you can also have a backward reflected wave. So that's a physical origin of having V0 plus, V0 minus. So now that we understand this, can we understand the sign to the characteristic impedance for the backward propagating wave? V0 minus divided by I0 minus is equal to negative Z0. Can any student try to answer this? If you get it right, you can have maybe 1 or 2 points for the semester score. This is a bonus. Can anyone try to explain this? Impedance taking a negative sign. Well, impedance can be complex. So -1 means you have a 180-degree phase difference. So it is valid, but the physical meaning is, if you want to understand the physical meaning, Are there any response? No response? Okay, you missed the chance to have bonus. Does anyone still remember P? Power. How is power related to voltage and current? Fill me clues. Yeah. P equals V up. Right? The things you learned in high school, but you forgot. P equals V up. So for the positive wave, P positive is positive. P negative, under this definition, is negative. Right? So under this definition, the negative propagating current amplitude is 180 degrees out of phase with the voltage amplitude. And therefore, its associated power is negative. So you have to think, does that make sense? It makes perfect sense. Because if you still remember, in your electric circuit textbook, in the very first page, it will tell you this book is using passive sign convention. Power is positive, means the power is wasted or delivered to you. So for type power, if it sends a positive traveling wave, it is losing power. But V times I is positive. So the positive power means it's losing power. From the generator, type power is sending this power to you. It's meant to be used by you. So type power is losing power. But that lost power takes on a positive sign. But if the user cannot use 100%, it returns some portion of the power back to the type power. Delivered takes on a positive sign, returned must have a different sign. So the power returned by the user to type power through the transmission line in the form of a reflected wave must have a V times I having a negative value. So the power returned or the power gained by type power must have a negative sign. So this is all taken care of in our derivation. So this is completely valid result. Right? Remember, power delivered to someone to be used, the power lost is positive, the power gained needs to be negative. So the reflected wave is like another small generator is sending power to type power, right? The power you cannot use. Right, so up to now, we are very happy. So through this relationship, we can somehow have, after introducing characteristic impedance, remember again, in characteristic impedance is the parameter intrinsic to the transmission line. Once you have a given transmission line, the voltage ratio for the positive propagating voltage to the current should be fixed. The backward voltage in current, they're also fixed, but only differing by a negative sign. Okay? So with the introduction and the understanding to transmission line, we only have V0 plus and V0 minus. remain to be solved. So the number of unknowns is now reduced to 2. Alright, so up to now, you might be asking, you've been doing all this derivation in the frequency domain, in phasor domain, which I'm not very good at. Okay, so let's transform the result back to the time domain, which is completely possible. Right? If you understand the definition, of phasor notation against the time domain parameter, so voltage as a function of space and time is a real part of the voltage phasor in the frequency domain as a function of space only, multiplied by exponential j omega t. Now, something you have to remember. V0 plus and V0 minus. These two amplitudes are usually complex numbers. Phasors usually have the amplitude and an associated phase. So I can somehow write V0 plus is having some amplitude and its own phase. V0 negative is having its own amplitude and its own phase. Okay? I substitute that back into the time domain. Eventually, this is what you have. In the time domain, you have an oscillating cosine wave propagating to the positive direction, and you also have a counter-propagating backward wave. It's also cosine form. But having this phase difference might make it a sine wave. Okay? It really depends. Is this completely new to you? On the transmission line, you have forward propagating wave, backward propagating wave. Is that new to you? What is the result? Something that you know, everybody here knows already. If you have counter-propagating wave on the same medium, you will have standing waves. Right? So mathematically, you have cosine plus cosine. So yeah, we're going back to junior high. Cosine plus cosine equals cosine multiplied by cosine, right? So eventually in the time domain, you have a standing wave. You have a standing wave. We will come back to this aspect in more details in the next part 7. So let us try to stop here, and I'm concluding the first PowerPoint set for transmission line. Do you have questions? If not, I am going to continue into the second PowerPoint set, which is more heavily mathematically involved. So, well, it depends on whether you perform the preview before the class. So do you have questions?